Hey everybody, so welcome to our first video in Unit 13, which is all about solutions. I am in a little bit of a different location today. I decided I'm going to film at school, so I brought all of my equipment to school. And this is probably where you're going to see the remainder of these videos. It's just a little bit easier now, especially with it getting dark so early. At least when I'm filming this, it's a lot easier for me to do this at school rather than in the dark at night. But anyway, so this whole entire unit is all about solutions. And we've worked with solutions before, especially in labs, but we really haven't talked too much about solutions and the properties of these different solutions. So that's what we're going to get into today. So what is a solution? Well, a solution is a homogeneous mixture that contains two or more substances that are not chemically combined. And that's a key part of a solution, is that they are not chemically combined. So, for example, if I have a salt water solution, I have salt and I have water. That salt, when it's dissolved, I'm not making something new. They're not being chemically combined to make totally new bonds. Sure, the salt is dissociating and forming ion dipole intermolecular forces, but I'm not producing an entirely new compound. All I have when I dissolve salt in water is I have salt water, right? And I can separate those components after I make the solution. And that's also an important part of that, is that I could physically separate these two components of the solution because they're not chemically combined. So here's just a couple of different colored solutions that you might have. It's interesting because many different transition metals will form different colored solutions. So a lot of times you know that you have a transition metal in solution, sometimes, is because transition metals tend to form colored compounds in solution. Depending on the charge of the transition metal, that's the color. We'll talk more about that, though, if you decide to take AP Chemistry. So what are the components of a solution, right? So we have these two parts. I have something that's dissolving in something else, and usually that something else is going to be water. So we have two components that make solutions. We have a solute and we have the solvent. The solute is whatever is being dissolved in the solution, right? And for the most part, that solute is going to be in much smaller amounts. So for example, if I am making a salt solution, the salt is my solute. I'm dissolving the salt in the solvent. And a lot of times you're going to have a much smaller amount of that solute than you are your solvent. So your solvent is your dissolving medium. Most of the time, your solvent is going to be water. And that's because water is very abundant, right? It has very unique properties that makes it very special. But whenever we make solutions in the lab, most of the time, that solvent is going to be water. Not always, but sometimes it will be. Most of the time. So now here's your example. So when I have salt right here, so I have my salt solute, and I add that to water, which is my solvent, I produce a solution. And this solution retains the properties of both the salt and the water. So you can separate the components of a solution using physical processes. So like I said, if we evaporate that water, we can get the salt back. That water retains its own properties and the salt retains its own properties. And that's a very important part of a solution, is that I do not have any sort of chemical change that's occurring here. All I have is that I have new intermolecular forces that are being formed. And there's a whole bunch of different kinds of solute-solvent combinations you can have. It's not just water, right? So we can consider all the states of matter and think about what are combinations of solutes and solvents. So a great example is the air that you're breathing in. So the air that you're currently breathing is primarily nitrogen, right? It's about 75% nitrogen, and among other things, there's oxygen, right? But those are the two usually primary components of the air. That oxygen is the solute because it's typically in lesser quantity, whereas your solvent would be your nitrogen. So the air that you're breathing in is a solution because it's made up of more than two different types of things that aren't chemically bonded to one another. They just exist next to one another. Can I separate the oxygen and the nitrogen? Sure, not in our chemistry lab, but we could technically if we wanted to using very high-tech equipment because they're not chemically bonded. So they're retaining their own properties. Can of soda, right? I have carbon dioxide and water. That gas, that CO2 is your solute. It's dissolved in the liquid solvent, like we talked about with gas laws. So when you have a bottle of soda, it's under pressure. So all of that CO2 is dissolved in that soda, but when you crack it open, that gas is able to escape, which is why it becomes less soluble as the pressure is decreased. Liquid and liquid. So alcohol and water is another example. Typically, we don't say that two liquids dissolve in one another. We say that they are miscible in one another. I can't really write on here too well today. I don't have my pad out, but we do say they are miscible. And that's because they have similar intermolecular forces, right? Like dissolves like. Alcohol dissolves very well in, or is miscible in water because they both can hydrogen bonds to each other. Liquid and solid, right? This is one I'm not usually too familiar with, but I guess there's some sort of dental fillings that use a liquid solute in a solid solvent. Of course, solid solutes in liquid solvents, that's our salt water, sugar water, basically anything we're making in the lab. Or we can have two alloys, a metal that's dispersed within another metal, right? Two solid phases of matter. And an example of that would be copper and nickel. So that would be like your brass. Steel is another alloy. Steel is an alloy of with a carbon solute and an iron solvent. Lots of different types of solutions. They don't necessarily have to be just solid solutes in liquid solvents. There's lots of different combinations. But let's go ahead and break down these solutes just a little bit more. These types of things that do dissolve in usually water or any different type of a solvent. So we can break solutes down into two categories, and there are electrolytes and there are also non-electrolytes. You've probably heard of the word electrolyte before because, of course, when you talk about Gatorade or Powerade, right, you're working out, you need a lot of electrolytes. And that's what we're talking about here are those electrolytes. So what does that mean? Electrolytes are substances that will dissociate and they form an electrically conducting solution. So when you are drinking Gatorade, you are drinking a lot of those charged particles that your body needs in order for your cells to function properly. So you're getting a lot of magnesium ions and sodium ions and potassium ions and chloride ions. All of that stuff is in the Gatorade, which allows your cells to work better, which maximizes performance. Of course, that's only if you're working out a certain extent, because you shouldn't drink Gatorade or any of that if you're not working out a lot, because if you're not losing those electrolytes, you don't need to replace them. It's only for a strenuous workout. So anything that dissociates and forms charged particles. So some examples of that would be soluble ionic compounds. So anything, I'll say most things that are ionic will in fact dissociate in solution. So like salt, for example. Salt is an ionic compound that will dissociate into sodium ions and chloride ions. And here's a nice little picture that represents this. So we'll notice in this flask, I have my solvent, which is, we're going to assume it's water in this case. And I have two particles that have broken apart to form charged particles. So here I have my positively charged ion and my negatively charged ion. And the same goes for here and here as well. So it breaks apart in solution. And because I have now those positive and negative charges, these are able to conduct electricity very, very well. On the other hand, you can also have non-electrolytes. So non-electrolytes, of course, do not do this. They do not dissociate. And because they're not producing those electrically charged particles, they're not going to conduct electricity at all. So some examples of this would be like very polar molecular compounds. Well, I won't say very polar, just a little polar. So things like glucose, right? Sugar. Sucrose is sugar, but glucose is, part of that, disaccharides. I digress. But sucrose and glucose, there are no ionic bonds there. So because there's no ionic bonds, it's not going to break apart in water. It dissolves because like dissolves like, right? And they have similar intermolecular forces, so they attract each other, but it's not going to dissociate. We do not form charged particles when these polar molecular compounds are dissolving. So yes, sometimes you could have substances like sugar that dissolves because of intermolecular forces, but it does not dissociate because we don't have any charged particles. So in solution, what does this look like? Notice the difference. This second flask right here, we have all of the particles that have not broken apart. So this is not an electrolyte. This is a non-electrolyte. If I was to try to run an electric current through this, I would not produce an electrically conducting solution because there's nothing for the electrons to essentially travel on in order to produce that conductive solution. Whereas here, I do have those charged particles that the electrons can kind of slide around on and conduct electricity. So two different types of solutes, electrolytes and non-electrolytes that dissolve in water, and they're basically categorized by how much they split apart and how much electricity can they conduct in solution. So on that note, let's talk about dissociation, right? So we just kind of talked about dissociating here. What does that mean? Dissociation is the separation of ions that occurs when ionic compounds or highly polar molecular compounds dissolve in a solvent. So dissociation, you are producing charged particles. So remember, dissolving, not producing charged particles, whereas dissociating, you are producing charged particles. So, and in particular, it's the separation of ions. We are only really going to see this with ionic substances, which of course, as we know, are between metals and nonmetals. So if I have salt, right? Salt is an ionic compound. Salt totally dissociates into its ions. So if we were to write this equation out, I would have solid salt, and when it's introduced to water as a solvent, it dissociates into sodium ions and chloride ions. That's all I would write. This is the dissociation process that's occurring. I don't want to say reaction because I'm not making anything new. All that's happening is that they are separating from one another. That's dissociation. The only thing you really need to look for are to make sure that your number and types of elements are balanced on both sides. So for example, if I have calcium chloride, CaCl2, I would have 2 chloride ions that come off of that as opposed to the 1 for sodium chloride in this example. And we could see those NaCl particles that have dissociated in this figure. So right here, I have my positively charged ions. And if you look really carefully, you could see that I'm forming those ion dipole intermolecular forces of attraction, because notice how the negative oxygen side of water is facing the positively charged sodium on all three. So all three of these, the oxygen is facing the sodium because that oxygen is partially negative. Whereas look at here, we could see that all my positively charged hydrogens are surrounding this one. So this is a very nice diagram because it is showing that dissociation process very well. And we could see how the water molecules down towards the bottom start to arrange themselves so they can pick off all of those ions into the solution. Let's go ahead and take a look at this a little bit more and do sample problem 1 together. So we are going to write the dissociation for the following compounds in water, and then we'll determine how many moles of ions are produced from the starting number of moles. So let's start off with aluminum sulfate. So I have aluminum sulfate. I'm just rewriting this down here. And I'm going to write my arrow, but I'm going to draw water up here just to show that I'm dissolving this aluminum sulfate in water. And the dissociation of this, so I'm going to break that ionic bond, because as we know, ionic bonds will dissociate in water relatively well. And there are 2 aluminum atoms in aluminum sulfate. So this will dissociate into 2 aluminum ions, because aluminum has that +3 charge. And it will also dissociate into 3 sulfate ions. Forgot that 3. You're not going to dissociate these sulfur and oxygens, and that's because those are covalent bonds holding those together, and covalent bonds are not soluble in water, if you recall from the last unit. So in this case, we're only breaking apart the ionic bond. 2 aluminum ions dissociate from 3 sulfate ions. So we showed the dissociation, right? And this technically is balanced now. So 1 mole of aluminum sulfate will dissociate into 2 moles of aluminum. We'll write this down. 1 mole of that dissociates into 2 moles of aluminum and 3 moles of sulfate. So if I were to have a particle diagram of this, so let's try to draw a beaker. And if I had 1 mole dissociates, I would draw 2 aluminum ions, and I would draw 3 sulfate ions in there. It's a terrible drawing, but I think you get the idea. So I have 5 moles of ions that will dissociate from that. Let's backspace that guy right there. There we go. Okay. So the question is asking if I had 0.5 moles of aluminum sulfate. It looks like 1 mole of aluminum sulfate can produce a total of 5 moles of ions, right? So 1 mole of aluminum sulfate can produce 5 total moles of ions. So the question is, if I had 0.5 moles of aluminum sulfate, how many ions would I produce? Well, if this is half, right, a half a mole, I would only produce half of 5. So my answer is 2.5 moles of ions I could produce from that. And that's just a basic mole ratio. Let's go ahead and try the next one. So although this is not an ionic compound, this one is a very, very, very polar molecular compound. And I would tell you that in any equations that we do, just because we don't normally see these ones. I'm going to give you mostly ionic compounds to dissociate. But anyway, let's say I have hydrochloric acid, highly polar molecular compound. This is a very strong acid, which you'll learn if you take AP chemistry. But this guy will dissociate into 1 hydrogen ion, because of course there's only 1 hydrogen in hydrochloric acid, and 1 chloride ion, because again, there's 1 chlorine in hydrochloric acid. So we could write water up here if we want to. We could also write states of matter, but I'm not really going to worry too much about states of matter. I used to, but you know, College Board doesn't have you do that for AP, so whatever they don't have you worry about, I don't have you worry about. So all a 1-to-1 ratio. So it looks like 1 mole of hydrochloric acid produces 1 mole of hydrogen ions and 1 mole of chloride ions. So if I consider what's the total number of moles, it would be 2 moles. 1 mole of HCl produces 2 moles of ions. And this is going to be important later in this unit when we start talking about colligative properties. So the question is asking if I had 2 moles of hydrochloric, 2 moles of HCl, how many moles of ions would I produce? Well, if it's a 1-to-2 ratio, 2 moles of hydrochloric can produce 4 moles of ions. Just a basic mole ratio step. And here's glucose. So in this case, I have C6H12O6 right there. And I have water. We should also note that aluminum sulfate, this would be an electrolyte. There's ionic bonds there. This guy is a highly polar molecular compound. This is also an electrolyte. Sucrose, however, does not have very many very highly polar bonds. And it also doesn't have any ionic bonds. So this particular substance is actually a non-electrolyte. Non-electrolyte. And I'll let you know what are electrolytes and non-electrolytes. Because remember, electrolytes will dissociate into ions in solution, whereas non-electrolytes will not. So if this is not an electrolyte, if I have solid glucose that's dissolving, my product would just be this, C6H12O6. The state of matter, though, is not solid anymore. It's just aqueous. Sucrose or glucose does not dissociate. This dissolves. And that's because water and glucose have similar intermolecular forces. They both have London dispersion, but they both are dipole-dipole, and they both can hydrogen bond. But it's not strong enough to completely rip away any ions because there are no ions here. There are no ionic bonds. There are no very, very, very polar bonds in this case. I would let you know if there are very, very, very polar bonds. So in this case, if I have 1 mole of glucose that's dissolving, 1 mole of glucose comes out of that. I would have 1 mole of glucose that's dissolved, right? So the question is saying if I have 1 mole of glucose, C6H12O6, that produces 1 mole of glucose in solution. So the question is asking if I had 0.9 moles of glucose, how many moles of glucose dissolved would I have? It would still be 0.9 because it's a 1-to-1 ratio. I have to circle this guy up here as well. And that's how we have to take a look at dissociation, is what is this breaking up into in solutions? What ionic bonds am I breaking? Or what very polar molecular bonds am I breaking? So we're going to look more into this when we get into class next time I see you. As always, if you have any questions, please make sure you write them down and you ask me next time I see you in class. But otherwise, I will see you in the next video, which is all about solubility. Bye.